Nanotechnology in energy application. What is nanomaterial and nanotechnology? Nanoscale materials are those objects where the dimension, if measured then at least one dimension, is less than nearly 100 nanometers. A nanometer is measured as 1/1,000,000th of a millimeter, which is almost 100,000 times thicker than the diameter of a human hair. Nanomaterials generate huge interest for researchers as at nanosize of substances distinguished optical, magnetic, electrical, and other properties are surfaced. These newly highlighted properties have the ability for great impacts in electrical, electronics, medicine, and other fields. Dimensions between 1 and 100 nanometer are known as the nanoscale, on the scale of 1/1,000,000th to several tens of billions of a meter as shown below. Nanotechnology is creation of useful materials from the existing material by alloying them to make composite material or making them through control manipulation of 1 to 100 nanometer length scale, which induce novel properties into material in electrical, chemical, mechanical, optical, and magnetic domain. Nanotechnology is an emerging technology as researchers have seen great prospect into advancement of already established products by applying nanotechnology principles and developing wide range of new applications. Application areas of nanosciences and nanoengineering lie in the fields of pharmaceutics, advanced materials, electronics, cosmetics, packaged food, chemical engineering, precision mechanics, optics, energy production and storage, and environmental science. History of nanotechnology. Early contributors to the field include James Clerk Maxwell and Richard Adolph Zsigmondy. Zsigmondy studied colloids and looked at gold salts and other nanomaterials. Other important contributors in the first half of 20th century include Irving Langmuir and Catherine B. Blodgett, the first woman to get her PhD studying physics at the University of Cambridge. The term nanotechnology was used first by Japanese scientists Norio Taniguchi in a 1974 paper on production technology that creates objects and features on the order of a nanometer. The American engineer Eric Drexler is credited with the development of molecular nanotechnology, leading to nanosystems, machinery manufacturing. The invention of scanning tunneling microscope in the 1980s by IBM Zurich scientists, and then the atomic force microscope allowed scientists to see materials at an unprecedented atomic level. The availability of more and more powerful computers around this time enabled large-scale simulations of material systems using supercomputers. These studies provided insight into nanoscale material structures and their properties. The complementary activities of modeling and simulation, atomic scale visualization and characterization, and experimental synthesis activities fueled nanoscale research activities in the 1980s. The significant progress was obtained by IBM in 1990s when a team physicist had spelled out the letters IBM using 35 individual atoms of xenon. Another breakthrough came in 1985 with the discovery of new shapes for molecules of carbon, which known as buckyball, which are round and consist of 60 carbon atoms. This led to the discovery of a related molecular shape known as the carbon nanotube in 1991. Carbon nanotubes are still one of the most promising areas of nanotechnology, as they are about 100 times stronger than steel, but just a sixth of the weight. They have usual heat and conductivity characteristics. In parallel, studies of semiconductor nanocrystals led to the development of quantum dots, whose properties are between those of bulk semiconductors and discrete molecules. The major focus of research across the world continues to be research on nanoscale properties, synthesis of materials, and characterization and application development to create useful devices and processes and reap economic benefits. There is growing recognition of the importance of educating future scientists and engineers about this emerging field, as well as address safety and health aspects of nanomaterials. Nanotechnology in energy field. Nanotechnologies provide essential improvement potentials for the development of both conventional energy sources, fossil and nuclear fuels, and renewable energy sources like geothermal energy, sun, wind, water, tides, or biomass. Nano-coated wear-resistant drill probes, for example, allow the optimization of lifespan and efficiency of systems for the development of oil and natural gas deposits or geothermal energy, and thus the saving of costs. Further examples are high-duty nanomaterials for lighter and more rugged rotor blades of wind and tide power plants, as well as wear and corrosion protection layers for mechanically stressed components. Nanotechnologies will play this decisive role, in particular in the intensified use of solar energy through photovoltaic systems. In case of conventional crystalline silicon solar cells, for instance, increases in efficiency are achievable by anti-reflection layers for higher light yield. Solar energy. Photovoltaic solar cells are devices which produce electricity from the sun radiation by means of the photoelectric effect. The photons from the light are converted into electric current. The three critical properties that photovoltaics must have to be effective are transparency, conductivity, and catalytic activity. The increased surface area to volume ratio of nanoparticles should enhance solar energy collection and efficiency by exposing more conducting surfaces to the sunlight. Classic nanostructures such as carbon nanotubes, fullerenes, and quantum dots are being used to make solar cells lighter, cheaper, and more efficient. For example, constructing photovoltaics with vertical laying CNTs greatly increases the amount of light that can be collected. To improve solar collector efficiency, one of the most successful methods is substituting the absorbing medium water with high thermal conductivity fluid, which is nanofluid. Nanofluid is defined as the fluid containing suspended solid particles. Yousefi experimentally examined the consequences of aluminium trioxide water nanofluid on the efficiency of a flat plate solar collector. They observed the efficiency two different weight fractions of the nanofluid, including 0.2% and 0.4%, where the diameter of particles was 15 nanometers. Furthermore, they considered the effects of efficiency of Triton X100 employed as a surfactant. Their results are as follows: 28% improvement in efficiency by using 0.2% weight fraction nanofluid as compared to water. For a wide range of reduced temperature parameter, the efficiency of collector with 0.2% weight percentage nanofluid is higher compared to 0.4 weight percentage. Surfactant can enhance the efficiency by 15%, 63. Otanikar, another scientist, reported an experimental results on solar collectors based on nanofluids made from variety of nanoparticles such as carbon nanotubes, graphite, and silver. They demonstrated an efficiency improvements up to 5% in solar thermal collectors by utilizing nanofluids as an absorption mechanism. Advantages of nanoparticle solar power plants. First one, the extremely small size. The extremely small size of particles ideally allows them to pass through pumps and plumbing without adverse effects. Second one, nanofluids can absorb energy directly with exceeding intermediate heat transfer steps. Three, nanofluids can be optically selective. 4. A more uniform receiver temperature can be achieved inside the solar collector, which reducing material constraints. 5. Enhanced heat transfer by higher convection and thermal conductivity may improve receiver performance. 6. Absorption and efficiency may be enhanced by tuning the nanoparticle size and shape to the required application. Wind energy. Nanoscale processes, materials, and devices have already been introduced into the wind industry and contribute to the development of new standards for wind turbine performance, availability, operability, and reliability. Nanoscale models are being developed to prolong the lifespan of wind turbines, mitigate the fatigue failures of structural components, and lower the overall cost of energy generation. Nanocomposite materials with excellent strength to weight and stiffness to weight ratios are used to facilitate the development of next generation high performance blades. Nanoparticles are used to equip other materials with new properties in order to achieve novel functions. The synthesis of these multifunctional nanocomposites involves the use of low molecular weight polymers, the acetylenes, which generally have long-term stability and excellent processability. Nanolubricants with extremely low friction coefficients methodology have been developed to reduce energy losses in the rotating parts of wind turbine and maximize the energy system efficiency as a sophisticated protective line of defense. Nanolubricants use the geometrical surface of nanoparticles which behave like mini ball bearings to provide extraordinary anti-wear and protection. Fuel cells converts a fuel directly into electricity in an electrochemical reaction. Limitations of fuel cells. Hydrogen is costly and difficult to store. Fuel cells are often considered in the context of hydrogen because they convert hydrogen and oxygen to the water, producing electricity and heat in the process. Nano-optimized fuel cells. They use platinum nanoparticles instead of solid platinum surface. Increases efficiency and allows much less metal to be used. Support platinum nanoparticles on a porous surface. Further increases the accessibility of the platinum surfaces. CNTs may be important for composite components in fuel cells because of high strength and toughness to weight characteristics. Hydrogen energy. Hydrogen is the smallest element. It can escape from tanks and pipes and more easily than conventional fuels. There are two ways to store hydrogen in materials. One way involves absorption of hydrogen within material, and the other is to store hydrogen in a container. The challenge for absorption is to control diameter of nanotube so that the absorption energy of hydrogen on the outside and inside of the tube is high enough to provide the desired storage capacity at an acceptable pressure. If the absorption behavior of optimized tube is acceptable, the challenge then is to develop a process capable of producing the material at a reasonable cost. Single-volt CNTs are leading candidate for solving the storage problem for hydrogen-fueled cars and trucks. However, if this approach cannot be carried out, CNTs could still facilitate storage in a container. Small hydrogen-fueled vehicles would have pressure tank, and large hydrogen-fueled vehicles, ships and planes would have a cryogenic liquid heat hydrogen tank. In this case, CNTs may be used in super strong composites in the bodies of the vehicles to make them lighter. Nanobatteries. CNTs have extraordinarily high surface areas and good electrical conductivity, and their linear geometry makes their surface areas highly accessible to a battery's electrolyte. These properties could enable CNT-based electrodes in batteries to generate increased electricity output as compared to traditional electrodes. This ability to increase the energy output from a given amount of materials means not only the batteries could become more powerful, but also that smaller and lighter batteries could be developed for a wider range of applications. In April 2006, a nanotechnology company, Altair Nano, owner testified before Congress about a new nanotechnology battery with potentially broad applications. The battery technology utilizes 25 nanometer nanostructures, lithium titanate spinel, as the electrode material in the anode of rechargeable lithium-ion battery, replacing the graphite electrode typically used in such batteries and contributing to performance and safety issues. The new battery offers vastly faster discharge and charge rates, meaning that the time to recharge the battery can be measured in minutes rather than hours. The nanostructured materials also increase the useful time of the battery by 10 to 20 times over current lithium batteries and provide battery performance over a broader range of temperatures than currently achievable. Over 75% of normal power would be available at temperatures between -40 Fahrenheit and plus 152 Fahrenheit. Other commercial applications for these batteries are for uninterruptible power supplies (UPS) and emergency backup power. Present-day UPS and EBP systems typically use lead-acid batteries because of their reliability and low initial cost. However, lead-acid batteries must be replaced every 2 to 3 years, and hazardous materials issues surround their manufacture, handling, and maintenance. Lead-acid batteries also lose charge quickly in extreme temperatures and suffer from power declines and a decreased ability to accept a recharge over time. By comparison, prototype batteries using nanostructures lithium titanate electrode material show promising improvements. Advanced lithium-ion battery is virtually unaffected by temperature extremes. Its charge is fully available immediately and it can accept a full recharge in a few minutes. It also has a much longer lifetime with no decline in performance, and there are no hazardous material issues. With these kinds of advantages, UPS and EPP systems could become more reliable components of distributed mini grids. Advantages: nanotechnology in energy. Nanomaterial coating can prevent the corrosive materials from corrosion. They decrease the frictional tear and wear losses, thus they increase the efficiency of the system. They are extremely lightweighted but are harder than materials like steel, iron. The plenty of raw materials are available for the manufacture. They are durable for a number of years. Disadvantages: nanotechnology is very expensive as its production cost is high. Impact of nanotechnology on the environment is still unknown. Thank you for listening.